Hey everyone and welcome. I'm very excited to have Sebastian Bidegain with me. Welcome.
Hi, thanks.
So Sebastian is a fourth year medical student just about to graduate, so congratulations.
Thank you.
And he has been on an elective with us working on MedEd innovation and MedEd design using our digital media maker lab. And you are one of our first students to come join us, so I was very excited when you decided to do this.
Thank you.
So we're going to showcase his project, which I think is amazing, and we're just going to go through how he came up with it, how he designed it, and just ask him a few questions about all of his work. And then when we're done, we'll go ahead and throw this all up on our website, step-by-step design profiles and a bunch of information, so that if you wanted to sort of follow along with the same model or develop it yourself or continue on, this is an open source project. So Sebastian, welcome.
Thanks.
Cool. So why don't we start off by just talking about how you came up with the idea and what you wanted to accomplish.
Totally. So my favorite subject to learn in medical school was neuroanatomy. I liked how it was very clinically relevant. Sometimes in anatomy things were just anatomy, and then you eventually learn the clinical things later. But with functional neuroanatomy, everything was clinically related. And I also found it very challenging as well. So I thought it would be a good, there's a lot of really cool diagrams in the textbook, and I thought it would be a really great project to do a design project for, maybe try to make a model and improve something that I thought as a student was kind of hard to learn.
Yeah, I love that you picked this. I remember as a medical student struggling with this schematic, that diagram of all the visual field cuts. And I kind of always wished it was a little bit more interactive so that I could actually, instead of just looking at a diagram or a schematic, I could actually see how it worked. Mm-hmm. So that was really your goal, right? To kind of make that schematic come to life and make it more interactive for learners, right?
Yeah, absolutely. I wanted to make it interactive, like you said, and I also wanted to incorporate light. A personal goal for mine as well was to kind of like learn a little bit more about digital fabrication skills, a little bit about programming and how to incorporate animation and more interactive things into medical education models.
Yeah, so you really had a dual purpose. One was to teach yourself something and to teach others something, but then also teach yourself skills to learn how to teach in new ways, and maybe then bring that into how we learn in medical education. So I thought that's really the mission of the Digital Media Maker Lab here, the MedEdge Studio. So I think it was perfect that you came and joined us.
Thank you.
So let's go through this. So tell us a little bit. So where did you start in this design? Like what were the things you were first thinking about?
So the first thing I was thinking about actually was I was flipping through my old neuroanatomy notes, and I had a drawing that I made actually, and it was a schematic of the visual field defects. And the image from the textbook really stuck in my mind, and the way that I learned it was I just wrote it down, which is like, I guess, how you learn a lot of things in anatomy. But I thought that it could be improved slightly and making it interactive. With this model, actually, so it basically, where should I start?
Well, why don't you start? So, I noticed this right off the bat. So this was your first attempt, right? This was your first kind of schematic. So tell us a little bit about this. What tools did you was to just create that? Because it's kind of cool.
Yeah. So this, I actually used an image from the textbook, from the clinical neuroanatomy textbook. This was kind of where I started here. I used Adobe Illustrator and I traced it. And then I used a laser cutter and I cut it out of cardboard. But what this diagram is illustrating basically is how the visual system is wired. So how input goes from the eye, from the retina, all the way to the back of the brain, and where after it's processed. And basically there are several different places along the path where things can go wrong. And if there's a lesion there, it produces a characteristic type of blindness in a certain eye or a certain region of the eye or in both eyes. And it is complicated to how all the wires connect, but it's actually pretty intuitive if you walk through it. But by walking through it, you need to go from the retina and follow the path that each nerve is taking. And so I thought it would be a good way to isolate each region, each nerve, and have a way to illustrate what each lesion looks like, and you can then kind of like trace it back to the retina where you can understand it a little bit better.
So, so after you got the schematic and you basically took the schematic off the digital world and then put it into a laser printer and then cut this out on cardboard, which in and of itself I think is really cool. You basically made the schematic pop off the page.
Yeah.
So you used the laser cutter for this, and this was kind of the jumping off point for what we're gonna, did we lose our?
It's still going.
Oh, it's still going, okay. Well, we'll cut that part out. So after you finished with the laser printer, that was really the jumping off point for the more complex model that you're gonna walk me through now, right?
That's correct.
Okay, cool. So why don't you show us where you ended up and how you ended up there?
Sure. So first, I should probably explain a little bit how this is working. So this is the model. This is a cross-section of the brain, like going like this way. These are the eyes. This is the thalamus. This is the back of the brain, the occipital lobe. And what you're seeing here, it's labeled. So you have the retina here, the optic nerve here, the optic chiasm, the optic tract. These are the lateral geniculate nuclei, and then optic radiations, and then it goes all the way back here to the occipital lobe. So
you basically used a laser print cutter
laser, yeah.
to sort of basically carve this out and then raise it, right? And then the LEDs are embedded within it, and so then you have basically this schematic now in this raised out 3D model.
Yes,
Very
that's
cool.
correct. So this is like a thin sheet of wood. The cool thing about a laser cutter is you can cut, or you can engrave, or you can do anything in between. So you can make you can shade things, you can do a lot of different things. So what I did here was I cut the outline of the brain, and then I lifted it off of the model a little bit, and then I also engraved different shapes and stuff. So here you have labels here, and then labels for the different lesions as well. So just to kind of walk through the path that the light takes from the retina to the back of the brain, it's going to enter the eye through each retina, and this is the left eye, this is the right eye. Where it starts to get tricky is immediately when the light enters, the left part of the eye is actually looking at the temporal side of the vision. So this half of the eye is looking at everything on this half of your vision, and then this half of your eye is looking at everything on the nasal side, so on this half. So immediately you have like a laterality within each eye. So I outlined that by using different colors for each side. So the nasal vision of each eye is green, and the temporal vision of each eye is blue. So after that, it's going to pass through the optic nerves of each eye, and then it comes to the optic chiasm, and that is the first point where it can get kind of confusing because you're having one of the parts of the optic nerves that's containing information cross over. So once you reach this point, now you've established laterality of what you see in each eye. So now all the temporal view of each eye, so like the outer part that you see in each eye, is now going to one side, and the nasal part of each eye is going to one side of the brain as well. And you can see that by the color switching. Once it reaches the lateral geniculate nucleus, then it's going to create optic radiations that are going to come out and then go towards the occipital lobe. One thing that it was also kind of hard to understand, so at the optic chiasm, you're having the temporal and nasal side split from left and right brain, but at the lateral geniculate nucleus, you're also having the image split from superior and inferior. So everything that is on the top half of your vision is going to go on this upper one, and on the bottom half, it's going to go on this lower one. They eventually converge again, which is shown here, and then they split into different parts of the calcicrine sulcus, which is here.
So basically what we're seeing here is the anatomy as it is in a non-pathologic, normal, standard state, correct?
Yes.
Yeah, I mean, it's amazing how, I hope it shows up on the video, how cool it feels when you look at it in person. It makes you want to kind of play with it and touch it, which is kind of, I think, the point.
Totally.
I also noticed that you have a really great understanding of this now. So I'm assuming that doing this project, really embedded this in your brain. Like if you never take anything away from your functional neuroanatomy, you're always going to remember these.
Yeah, hopefully I never forget this.
Yes. All right, so now that we've gone over the basics, go ahead and show us how you would use this to learn about all the various anatomic lesions and what kind of visual field deficits they would create.
Okay. So this is the one button that you have to press, and it will basically shuffle through all of the lesions. The lesions are here. You can see are labeled A, B, C, D, E, F, G. The first button you press will highlight the lesion, so you'll see a red light turn on here. That's the site of the first lesion. When you press the button the second time, it's going to show you what areas are affected. So it's going to highlight in red all the areas all the way to the retina, from the lesion to the retina that is going to be affected by a lesion there. So you can see if the lesion is here in area A, it's going to affect this entire nasal half of the vision of the right eye. And you can shuffle through. So B, you can see it's a lesion in the optic nerve. And when I click it again, it's going to backtrack all the way back up, and it's going to affect the temporal and the nasal vision of this eye as well.
So just so I'm clear, so you press it the first time and it shows you where the lesion is.
Mm-hmm.
And then you press it the second time, it shows you what the effect of that lesion will be on the visual field.
That's correct.
It's very simple, but I think it's really dramatic, and like just looking, oh, there's optic nerve. It's going to affect that whole eye, that whole visual field right there. But I think, as we go down, it gets more complicated, which is what I love about this. Is let's go through let's keep going through the cycle and see what we see.
Sure. So now we have a lesion in the optic chiasm, and you press it again, and then actually the effect is going to be that it takes out vision in both eyes, but only in the temporal half. You can keep going through. And that's all of them for now. It's still a work in progress. There are some other lesions I wanted to highlight as well, but these were the first few.
I mean, I love this model. It's a lot of fun. I've been playing with it since we came up here this afternoon and you first showed it to me. Let's take a brief pause here, and then let's dive into a little bit of the guts of the machinery and how you actually built it to make it work, and then some of your future directions.
Okay.
That's great. All right, Sebastian, let's get into some of the underside of this. Show us how you actually created this and used all the electronics.
Sure. So I'm just going to unplug it first. Okay. So on the back of this, it's going to look kind of crazy. I have a Arduino and some breadboards. So the Arduino is a microcontroller, and that is what is controlling the LED strips. It has the code, the program that I wrote, that basically shuffles through all the lesions and tells what intensity of light that needs to be displayed, what color, whatnot. The LED strips are from, they're called Adafruit NeoPixel LED strips. There's 2 of them. And what's cool about them is they're actually side lit. So the side of the LED strip is actually what the LED points up at, because normally you have an LED strip and the flat part is what's shining the light, so you can't actually get like a bendy shape without the light pointing left or right. It's actually going to be pointing up, as you can see here. Then I have everything kind of wired together. They're all connected to these breadboards, which allow you to plug things in and unplug them without soldering it, so that you can prototype, you can see if it works. Nothing's permanent. I have a 5-volt power supply here for the LED strips, and it's attached to a capacitor here as well. The LED strips need 5-volt power. If you go higher than that, they could get damaged. If you go lower than that, then they need to, they won't be bright enough. They might not work, actually. And then separately is the Arduino is also powered as well, but it's powered by my computer that allows me to write to it and write the program Ideally, I would connect the two, but because the power supply for the LED strips was really finicky, I didn't want to mess with that at the beginning. I have a piece of cardboard here that I was originally prototyping with, and that's what I glued everything to, and I was able to poke holes and feed the wires through the back, and I eventually stuck that onto this wood panel that I laser cut. Inside of here, I don't know if you can see, but it's actually elevated a little bit, and there's a white 3D printed little enclosure that I have that is holding the LED strips into the shape that they are in right now. That I designed in Fusion 360, and I 3D printed it to fit. I took a picture of it, and I traced it and scanned this. I traced this shape so that I can cut it out of wood, so that after gluing the LED strips down, now I have a shape that exactly opens up for the LED strips here. I also added this laserable plastic that I put to protect the strips from popping out, and also add a little detail, like it says nasal and temporal here, so you can kind of see what's going on. And then it has some lines here that look like nerves to kind of illustrate these optic radiations. I also have a button here that's hooked up. This is the button that controls it. It's fed through the back and plugged into the Arduino as well. Yeah, and I just kind of built this box so that it stands, and the bottom parts are not scraping against the surface of whatever you have it on.
Cool. Well, I'd venture to say this is a really incredible piece of MedEd design. So tell us. So we have our MedEDge Lab here, and we're in the process of creating the Digital Media Center as well as the 3D Maker Lab. But you worked with Nidhi Parikh from Cornell Tech in the Maker Lab on a lot of this, correct?
Yes, that's correct.
Okay. And what amazes me is not only just what you created, but also this idea that we can move beyond medical education skills being just making PowerPoint slides or recording short videos, right? That you can actually use materials like laser printers and 3D printers and some basic electronics to create something as wonderful as this and as interactive as this. So I really hope that this becomes inspirational for others who want to make medical education better, and sort of take this design as an example of what's possible. I want to ask your experience on it. Did this feel like incredibly daunting, or did you feel like it was doable? I mean, clearly you've made a lot of progress, and I know you want to do more with it in the future. But did you feel like getting to this point was something that was something that you felt capable of achieving?
So it was going to be a 10-week project. I actually had been a little bit more ambitious with it, thinking I could do like a camera and create like blind sections of the vision, so you like actually see as what the patient would be seeing. That was my original idea actually when I was in anatomy, thinking I was like, oh, what does it actually look like to be blind in like half of one eye? It's hard to actually conceptualize that.
Right.
I wanted to do that. That was way too complicated for the time, so I actually had to scale back a lot. I also wanted to illuminate different types of the output of different types of blindness that you could see here.
This here, right, is meant to be backlit, right, and have the various visions of what you see and the kind of types of visual field deficits when you click on this, and they're supposed to connect together.
Right.
Correct.
And that was also the hardest part was learning the Arduino, the electronics part, making the circuit, and then also writing the code and the limitations of the Arduino as well. That was kind of the hardest part. And I had a friend, a classmate here, Lauren Mock. She helped me so much with it. I don't think I could have completed that part without her. So I'm really thankful for her help. Yeah. And that was the hardest part. I think if I had some more time, I could make multiple buttons maybe, or add more features. But the laser cutting, the 3D printing, I had been a little bit familiar with before, so that was kind of what I entered this project thinking a majority of it would be. So it didn't seem too complicated, but the learning experience I got from the electronics was a lot.
Cool. Yeah, I think tackling coding, I'm intimidated by it, but I feel like more and more, the ability to write simple code to be able to create models like this is I think will be the future. I do think that it will be something that's taught in medical education courses, as learning to be great educators also includes maybe coding. So you're pioneering the way for us. Thank you.
Thanks.
I want to thank Nidhi Parikh and the Cornell Tech Maker Lab for assisting in developing this.
Thank you, Nidhi.
Yeah, thank you, Nidhi. But thank you so much for giving us the demonstration. Remember, everyone, all this material is going to be open source and up on our website, so we'll give you all the information. You'll be able to watch this video and then have all the schematics and some information for you to kind of see what Sebastian's done, and then maybe take it into your own space as well and play around with the idea. All right, Sebastian. Thank you very much. You accomplished so much in 10 weeks. I'm so impressed.
Thank you.
All right. Bye, everyone.